Well, good afternoon to everybody who already has joined our seminar. Well, let's give another 2-3 minutes to our colleagues to join the seminar. Well, especially let's give 2 minutes to participants of the team leaders meeting, which has just ended at Sano, and then we will start our seminar. It will be the last seminar in this winter semester. We'll have a break until more or less middle of February, and then we will resume. But anyhow, let's wait yet another minute. Well, okay. So it seems that the number of participants is more or less stable. Well, and so we can start. Today, as a speaker, we have Dr. Marek Wodziński. Marek is employed at 2 places, at AGS University of Krakow, and also he is a postdoctoral researcher at Sano in Valais in Switzerland, in a very nice place. Marek has a quite long, good experience in such areas like medical imaging, like medical image analysis, computer vision, and also in deep learning. And he is principal investigator in many international research projects. Well, and he also was awarded for his papers at a number of conferences. And well, today Mark promised to give a talk about modeling of personalized cranial implants in real time, modeling based on artificial intelligence. So, as usual, if you have an urgent question, you can ask this question with questions and answers or chat. I will try to transfer this question to Marek. And of course, after Marek's talk, we will have, as usual, we have a discussion after his presentation. So, Marek, screen is yours.
Okay, thank you for the kind introduction. I'm Mark, and I will present you today the Deep Implant project that was awarded by the SBR, the National Agency, the Center of Research and Development. We got this grant in 2023, and this is an ongoing project that is going to take three years. So thank you for the opportunity to present this during the Sano seminar, and I will introduce you to the project. We'll show you the current results and our further research plans. So let's start from the very beginning. What's the idea behind the Deep Implant project? So the goal of Deep Implant project is to perform automatic skull reconstruction. What does it mean? People nowadays undergo a lot of cranial damages, for example, due to warfare, especially important now because of the war in Ukraine, but also traffic accidents and also some complications after, for example, surgery. The problem is quite urgent because the people after such cranial damage, they need to wait sometimes even several weeks for the reconstructive surgery. Here, we plan to propose a system that will automatically reconstruct the cranial cavity, the full skull, using segmented skull as the input to the system. In the project, we plan to not only propose the personalized implants, but we also plan to perform this in real time and to allow the doctors, the surgeons, to see the results, to examine the results in mixed reality before the 3D printing that can happen directly in the hospital performing the reconstructive surgery. What's the motivation behind this project? The motivation you can basically see here. Living without part of your skull is quite, I would say, problematic. It's not convenient, and we simply want to make the life for the people easier and less traumatic. Every year, there are around 14 millions of neurosurgical interventions each year. And worldwide, there are about 23,000 of neurosurgeons missing to meet only the most pressing surgical needs. And unfortunately, if the surgery is not performed, it's very often people simply die. This is especially important for the less developed countries, where the number of doctors is significantly lower. However, still, even in countries like Poland, like Western Europe, people need to wait several weeks before the reconstructive surgery, which significantly lowers the quality of life. Moreover, the project has also quite important economical implications. In the USA, the median salary of neurosurgeon is more than $500,000 per year, about 2 million zlotys per year. And a single neurosurgeon, on average, performs 150 more or less operations per year. And that gives you more or less the overview what's the cost of the human power, of the human resources to just run one single operation. Moreover, of course, not only one neurosurgeon is present in the operating room, we also need to pay for the operating room facilities, also all the other personnel, etc. So it is extremely costly procedure. And here in this project, we want to enable the 3D printing of personalized cranial implants directly during the primary procedure. So, for example, just after the traffic accident, just after some different source of cranial damage, to directly, in one single operation, save the people's life and to close the cranial cavity by printing in real time the personalized cranial implant. Obviously, it's not possible for every type of skull damage. However, we estimate that for at least 40% to 50% of the cranial damages, it is possible to perform the reconstructive surgery directly during the primary surgery. Before starting the project, before applying for the funding from the National Center of Research and Development, we had to obtain some initial results to show that the topic is promising and that we can get quite good results. And we started from taking part in a challenge that was organized during MICAI 2021. It was called Auto Implant Challenge. And apparently, we won the challenge in all on the tracks, in all 3 sub-challenges. Our solution based on linking data sets was the most successful. We basically proposed that it's much more important to understand the data and to use this data properly instead of proposing, let's say, very advanced neural networks, advanced neural architectures. Then we extended this initial work into a journal paper published in Computer Methods and Programs in Biomedicine. And having these 2 papers and this one challenge, we apply for the funding from the National Center for Research and Development because this showed us that actually it's extremely huge topic that can lead to significant advances in numerous fields. So we decided that after these 2 papers, the work is still not done. To show you the initial, I would say, stage of the work, we prepared a short video. So basically, this shows you what we developed before starting the project. We developed a system that automatically reconstructs the cranial defects and that enables one to show, to present the reconstruction in a mixed reality. Here, actually, we showed this visualization using external software that was made available for us by a nice company, MedUp SA. However, right now we are developing our own software for this. So after we presented this during one of the neurosurgeon conference, we got a lot of questions, basically, where they can buy this product. And unfortunately, the product is still not there, but it motivated us even more to work on this project and to really deliver something, technology that is ready to use in practice. Okay, now I will switch to the things that we are currently doing, that we partly finished in the project, and will show you 4 topics that we addressed during the realization of the deep implant project. So the first topic will be about reducing the memory usage by using point clouds. So this will show a thing that we published during MICAI 2023 conference, presenting the work entitled High Resolution Cranial Defect Reconstruction by Iterative Low Resolution Point Cloud Completion Transformers. What's the problem? Actually, high resolution computed tomography exceeds resolution equal to even 512 cubic voxels. And this is beyond the memory capabilities, even for large, high-end GPUs like GH200 available in a Helios supercomputer. Moreover, personalized implants, they really require sub-millimeter precision during modeling and manufacturing. So downsampling is unfortunately undesired. And moreover, patch-based approach that is very, I would say, popular in image segmentation is not optimal here in this research, because here we directly need global context, and we need the global context at high resolution. So we propose an approach based on geometric deep learning based on point clouds. We proposed a method that reformulates the problem from the standard traditional volumetric segmentation into point cloud completion task. So firstly, we started from taking the 3D volume presenting the segmented skull. We pre-process this to get the point cloud presenting the skull, and then we propose that it may be very wise to split the point cloud into coarse groups to basically reduce the GPU memory requirements. And then we trained a point cloud transformer based on the PointNet++ architecture. We also extended this by some parts of the point transformer architecture that basically performs the reconstruction on very low resolution, taking as the input just several thousands of points. However, thanks to using point clouds, actually, which are unordered set of points, we could perform this task basically in parallel, iteratively, for each group, strongly limiting the required GPU memory. And after that, we can just concatenate all the reconstructed partial point clouds, resulting in very nice result in terms of the reconstruction quality that is ready for meshing, that is required for the following 3D printing, or transferring it back to the voxel domain to perform, for example, additional post-processing. Here you can see how this looks qualitatively. That's on the left, you see the ground truth. Here you see the result of using directly the point transformer. Here for the comparison have volumetric network that downsamples the representation and then upsamples it back to the original resolution. And here you see the proposed method, the results of the proposed point cloud-based iterative reconstruction method that outperforms all these previous approaches. And our method, even though quantitatively it is on par with large-scale volumetric networks, it required just more or less 3 GB of GPU memory, and basically it was independent on the resolution. In contrast, when compared to the volumetric networks that even for downsampling, they required something like 20 GB of GPU memory, and some of them even could not fit into the GPU memory. So that presented us that indeed the geometrical learning here is a very good prognostic, very good way to develop this type of methods. However, we noticed that the problem that the point cloud representation has significant problems with respect to recovering fine details that are better reconstructed using the volumetric approach. So that's why currently we are investigating a combined approach. So we are developing surface mesh based reconstruction. Another topic that we are exploring in the Deep Implant project is related to the generalizability of the methods. And the first approach that is basically quite obvious is to use the data augmentation. So the content on the following few slides comes from one of the papers we published from the project. So it was published in Computers in Biology and Medicine that explores a very heavy data augmentation to improve the generalizability and also the quantitative results for the defect reconstruction. And why it's important in this particular project? Firstly, this project is quite unique because here we cannot acquire real ground truth. Because to have a real ground truth, we would need to have CT scans acquired before and after the cranial damage. And it's obvious that we can acquire the CT scans after the cranial damage, but we simply cannot acquire such scans before the traumatic event. So we cannot define the real ground truth, so we don't have the skull before the the traffic accident or different source of cranial damage. So we must rely on synthetic data. Then the number of high-resolution scans with open data sets, with appropriate bioethic committees licenses is quite limited. Up to now, there are 4 such data sets, and the largest of them has just few hundred volumes. Moreover, the school, even though it is not obvious, but school is also quite heterogeneous, especially the school defects. They are very heterogeneous because they may be different field of views, different resolutions, and the defects may be placed in various positions on the human head. So to solve all of these problems, we proposed an approach based on very strong data augmentation. Also, I would say not trivial data augmentation that significantly improved the generalizability. So I suppose that majority of you are already familiar with the basics of augmentations, for example, the geometric augmentation. The geometric augmentation simply applies some random geometric transformation like shear, like scaling, rotating, translating, etc. To on the fly during loading the data to create some new sample. I would say maybe not a new sample, but a modified version of the currently existing sample. But there are also more augmentation methods that can be used. So here we also explored the image registration based augmentation. It is not only augmentation. It cannot be performed during the data loading, but it can be performed basically offline. So during the dataset preparation stage, it takes 2 or more volumes and applies deformable registration between these 2 volumes to create some intermediate representation. And if you have, for example, data set of 1,000 cases, if you register all cases to all cases, then you basically result in 1,000 squared size data set. And this is a very nice thing, as long as the data sets have similar morphology. So when the image registration can be simply applied. Apart from these 2 geometric augmentation methods, we also explored several others generative augmentation methods. For example, based on the variational autoencoders, where we trained a network that then simply from the noise generated new synthetic samples. We also trained a network based on the Wasserstein generative adversarial networks. We also tested the vector quantized variational autoencoders to limit the negative influence of regularizing the latent space. And we also tested the latent diffusion models, combined both with the variational autoencoders and the vector quantized variational autoencoders to verify whether the diffusion process is beneficial for generating new synthetic samples. And we also combined all of basically these strategies together. And it turned out that actually, yes, for this particular project, data augmentation is something that must be applied. Without basically geometric augmentation, as you will see in a few slides, we simply cannot generalize to real, previously unseen cranial defects. It turned out that applying very extreme, I would say, geometric augmentation, so flips across all axes, random crops, a very strong affine transformation, and also adding binary noise improved the results the most. Moreover, we verified also the influence on the offline augmentation strategies on the number of generated cases. And some very interesting observations were observed that majority of the generative methods they very quickly saturate. So for example, when we attempted to use a version autoencoder, intro version autoencoder, soft intro version autoencoder, and also wgen, all these methods, they saturated quite quickly and generating number of cases beyond a certain threshold was not improving the results anymore. However, in contrast, using the vector quantized VAE, as well as the latent diffusion models, but what's very important, based on the vector quantized version of the autoencoder, as well as image registration, then we have not observed this kind of saturation, which suggested to us that using any kind of sampling based on sampling the normal standard distribution is not beneficial for augmenting data sets. In contrast, generating new samples using non-regularized latent spaces is much more beneficial. We also explored the impact of the image registration because one of the most important parameters in image registration is the regularization coefficient, and that controls the smoothness of the deformable registration. And here we observed a very nice thing that actually for augmentation, applying the registration is, I would say, in contrast to applying registration in medical settings. So here we actually want to achieve incorrect registrations that breaks the skull or defect morphology because it improves the data heterogeneity. So lower regularization coefficients resulting in folding improved the quantitative results much more significantly compared to a very smooth regularization coefficient that resulted in good registrations. We also compared two sampling methods for the generative networks based on sampling the standard distribution. We compared the pure random sampling that is used in majority of the papers that are about generative augmentation. We compared this to something called university density sampling that we proposed. It's an optimization procedure that basically optimizes the latent spaces to be more or less uniform in the latent space. And we basically shown that using the uniform density sampling improves the generative outcomes for all the generative networks that are based on the sampling. And finally, we combined different sampling strategies, different augmentation strategies. And here you can see a huge improvement when using very strong data augmentation that is combining both the online geometric augmentation, the image registration based augmentation, and the latent diffusion models based on the vector quantized version autoencoder. These results compared to the baseline without any augmentation is basically more than 0.1 in terms of dice, and the improvement is also very huge in terms of the Hausdorff distance or mean surface distance, resulting basically in perfect reconstructions. These quantitative results are basically ready to be used in medical settings in real-world applications. However, these quantitative results they do not show actually everything, because these two data sets they consists of real skulls but with synthetic defects. So that's why we decided to also show the impact using real cranial defects in real skulls. And here you can see this. These are two different data sets, exemplary skulls of two different data sets presenting real skulls with real cranial defects. That's the input skull. And here you see how the neural network reconstructing the skull behaves where there is no augmentation. And actually here you can directly see that without any augmentations, we are basically almost always wrong. So here we have only one single correct reconstruction. And that's something that you don't see in the quantitative results, but because still here the 0.84 looks like something useful. However, actually it's not, because it does not generalize into different distributions. Using just geometric augmentation here, you can see that for these data sets, actually it improves the results quite significantly. 3 of the exemplary schools are reconstructed correctly, only 1 is incorrect. But here, in this data set, the geometric augmentation still is not perfect. The geometric augmentation alone is not improving the outcomes. Using just the generative augmentation based on the latent diffusion models is also improving compared to the baseline. However, alone, it's not really perfect. Still, you see some failures in the reconstruction. However, combining all of these strategies, so combining geometric augmentation, image registration-based augmentation, and the generative augmentation based on latent diffusion models, we obtain perfect reconstructions for all testing cases with real schools, real defects. Basically, no single failure, and we tested this on several different data sources from several different hospitals. However, still, even though we presented that this kind of augmentation is very beneficial, the thing is still not done, because we need to ensure that this particular technology needs to work for 100% cases. We cannot accept even a single failure, because eventually we would like to get medical certification for this algorithm. So we need to go even further. We need to handle out of distribution cases from distributions that were not observed, not seen at all during the training. That's why we proposed something called symmetry preserving, and this is a work currently under review in one of the journals. So data augmentation cannot basically address all out of distribution cases, because simply we can miss some possibility during training. Moreover, the generative augmentation that I have just shown you is very costly, and it cannot be performed online. Just to mention, we used more than 100,000 GPU hours to train all the ablation studies for the paper in Computers in Biology and Medicine. And sometimes you simply cannot predict what you will observe in practice. For example, here, that's something we more or less used for training, but that's, for example, something that we recently get for inference from one of the data sets. You can see that this looks completely different. Here you can see the full information about the human face and the human bones. The face bones that were not observed during training. However, still we need to somehow work and operate even for such cases. And to solve this, we proposed a very novel approach that we entitled symmetry enforcement. And what's the idea for the symmetry enforcement in our project? So basically, the baseline is to simply train some reconstruction network that takes as the input the high resolution CT scan. It can be, as we mentioned, a volumetric segmentation task. It can be a point cloud completion network, some surface mesh completion network, doesn't really matter. And we get some reconstruction. And if we would have a perfect neural network, then this would be the end of story. We would finish the reconstruction here. However, because we want to address also the out of distribution cases, and we propose this whole pipeline here around. So we introduced something that we entitled symmetry network. This is another second neural network that takes as the input a healthy skull. Healthy skull, it can be a full skull, it can be a skull with a deleted part of the facial bones. However, it takes the full skull as the input, and it learns the symmetry axis of the skull. And this is unsupervised process. We simply pass the skull through the symmetry network. We calculate the symmetry axis. Then we flip the school across the symmetry axis, and we calculate the dice coefficient between the original healthy skull and the healthy skull after the reflection. And we want to maximize the dice coefficient between this, because of course the human skull, they are not perfectly symmetric, but they are quite nicely symmetric, and apparently people even prefer to have symmetrical heads, because such people are considered as more attractive. This is the desired property, even though the symmetry is not perfect. We actually evaluated in the paper the maximum available symmetry, and the maximum available symmetry in terms of the dice coefficient was something like 0.97. So the skulls, they are not perfectly symmetric. However, we would like to have them symmetric. So we used this pre-trained neural network to regularize the reconstruction network during training. So to enforce the reconstruction to be as symmetrical as possible. Moreover, instead of just introducing this during the training of the neural network, we also proposed a secondary step that happens after the initial reconstruction. Because if we are just, I would say, partially correct, so if our reconstruction is more or less in correct position, occupies more or less correct space, then we can, using again the symmetry network, we can fine-tune the defect using instance optimization based image registration. So we perform iterative optimization that takes the reconstructed defect, combines it with the input skull, calculates the symmetry axis, and learns how to deform the initial defect to make the whole reconstruction as symmetric as possible. And this happens basically on the instance level after the reconstruction. And here we can perform this for each case separately. The displacement field is optimized for each case in separation. So that allows us that even if we are wrong, then we can still improve. The reconstruction afterwards to make the reconstructions as perfect as possible. And here you can see a comparison of the impact of the proposed approach. That here you can see some very large real cranial defect. It basically occupies almost half of the skull. And using just a baseline network, the baseline network simply fails. It's even better visible here in the 2D slice of this reconstruction. That is completely wrong. Something like this couldn't be implanted. But if we add our symmetry enforcement to this, especially the registration-based one, then you can see that the reconstruction starts to be close to perfect. In terms of the quantitative result, here you can see the comparison, the distribution of the dice coefficient for the baseline, for the segmentation-based symmetry enforcement, and for the registration-based symmetry enforcement. And here you can see a very visible correlation that the larger the defect is, the worse the performance of the baseline networks. However, if we introduce the segmentation and especially registration-based symmetry enforcement, then actually almost all cases lie between 0.90 to 0.95. That is basically completely acceptable from the medical point of view for the real-world applications. The fourth topic that we investigated so far is about skull segmentation. This is a research that was accepted for the Asian Conference on Computer Vision last year, and also the extended version of this paper is already under review. So the problem here is that skull segmentation is easy, but in computed tomography, in CT, but CT irradiates the patient, and nowadays basically MRI is preferred. We would like to avoid the irradiation of the patient during acquiring the school data. So we would like to be able to basically perform the reconstructions using MRIs. However, even though in CT it's easy, then it's absolutely not trivial in MRI. There are no data sets with ground truth available, and the heterogeneity of MRI is simply enormous. So one potential solution that we proposed is to perform MRI to CT modality translation using deep learning. So we propose the following pipeline. Usually MRI, but it depends, of course, but for this particular task, MRI is usually has a lower resolution. It's not always the case, but most often that's the case. So using low resolution MRI volumes, we transfer them into CT, then we apply unsupervised super resolution to get this synthetic CT on high resolution. Then we perform histogram matching with the ground truth CT dataset, and then we can simply perform thresholding using Hounsfield scale to get the segmentation of the skull from the CT scan. And for this, to achieve as strong generalizability as possible, we proposed a method based on the contrastive unpaired translation that was using not only the skull data, not only the head data, but basically all parts of the human body in unsupervised manner. So we basically acquired a very huge data set of CT scans presenting various organs, a very huge data set of MRI scans presenting various organs, and we trained using the supercomputing infrastructure, very big network to perform this translation. And we outperform other methods based both on deep learning, but also based, for example, of something called skull stripping that is maybe dedicated to a bit different task, but still some reviewers asked us that why we even do this if we can apply skull stripping, but apparently not. We cannot apply skull stripping for this kind of task. So that's something we already finished in the project. We have already published 5 papers so far. We have 2 papers in review and several other, I would say, in plans to send for review before the end of the project. And what will be our further future research in this project? So firstly, the reconstruction task, I consider this as a solved task. We have already finished the work on reconstruction because all our methods nowadays are the complete state of the art. We are the most accurate across all methods available worldwide. The strong data augmentation method on one of the data sets even acquired dice coefficient equal to 0.97, and we cannot go further. So this particular task we consider as already solved. However, reconstruction is not the same as personalized implant. Here you can see this very clearly on the picture on the left. This is a 2D slice of the top of the human head, and on the white you have the skull, the damaged skull, and on the red you see the reconstructed defect. And you see here that if we would like to basically insert this reconstruction into the human head, it would be impossible. Probably this particular damage was caused by some break of the skull bone, and the skull bone was basically breaking several pieces, and several pieces were taken out from the human head. Because here in one piece, we cannot simply insert this reconstruction, even though this reconstruction is very good, it's almost perfect, but we cannot perform surgery using just this reconstruction. We need to somehow transfer this reconstruction into personalized implant. And here we can see the process that the reconstruction alone looks like this, but we would like to propose something like this. So to be able to adapt the thickness of the implant, also the rim of the implant, to the material used for 3D printing, because different thickness will be required, for example, when printing from titanium, and different when, for example, when printing from PIC material. So we need to somehow adapt this to the potential material and the geometry of the cranial cavity as well. Another task that we started to investigate is to propose to implement dedicated three-dimensional web-based visualization tool where people can simply log in and verify and test the proposed reconstruction methods. So they can upload their own data set and verify whether the proposed method works for their data set, whether it generalizes into their cases. And we will release this test tool for free after it's developed. So everybody interested can simply log in and verify whether the software is useful for them. And that's why we decided to perform this as a web application. So it does not require any dedicated installation. People just use the web browser. Then we also plan to extend the mixed reality visualization to work as a plugin to the web application, so people can visualize the reconstruction both using just traditional screens as well as mixed reality devices, because that's something that is very desired by surgeons in the operating room, because they don't need to leave, for example, the clean zone, and there are several other reasons why it's beneficial to use mixed reality for the quick verification whether this particular reconstruction is useful. Then we also plan to perform 3D printing in terms of the developed implants. However, here we will mostly rely just on the geometrical validation, I would say. During the project realization, we do not plan for print from materials that have medical certifications, because firstly, it's beyond the available funding, and secondly, firstly, we would not need to find a patient and a doctor that would like to have such an implant. This is something we plan to perform after we conclude the project, after we have everything else ready, and then we will attempt to find additional funding sources to also bring this to real medical usage. I would also like to acknowledge the parallel grid infrastructure and CipherNet, because all of these computations wouldn't be possible without on the computing grants. We run the computation both on the Athena supercomputer and more recently also on the Helios supercomputer, especially the work on the image augmentation, the heavy augmentation based on diffusion models. That's something that we spent a lot of the Athena resources, and without this, we could simply never finish these experiments. And in the future, the future work will also be based on this infrastructure. And shortly about our research team, I'm currently the principal investigator in the deep implant project. However, we have also several other people involved in the task. We have Daria Hemmerling, that is our main, I would say, point of contact with all hospitals. He is responsible for the data management in the project. We have Mateusz Daniel, that is our senior software developer, also employed at AGH. He's responsible for the development of the application. We have Mirosław Socha, that is our 3D printing expert, responsible for all these 3D prints. And we have three younger experts, I would say. We have Kamil Kwarciak, that was developing the skull segmentation from MRI. We have Piotr Prichor, that is currently working on the defect reconstruction, but using surface mesh representation instead of the volumetric representation or the point cloud representation. And we have Richard, that is working together with Mateusz on the software that will work, that will visualize the project outcomes. And that's everything from me. Thanks for your attention. And if you have any questions, do not hesitate to ask me just right now, or afterwards. Here you have the contact details to me.
Many thanks, Marek, for your talk, full of technical details and let's say important from the point of view of applications. And well, now I open discussion, and we have the first person who would like to ask question. Olaf, please go on with your question, comments.
Can you hear me now?
Yes, now we can hear you.
Okay. Okay, so thanks for the interesting talk. I have a couple of questions, of course. Let's start by the last slide that you were presenting, the team. There was no neurosurgeon on that slide. So what is your, so how much is, let's say, the clinics in the loop besides, let's say, the exchange of data that you explained with Daria being the point of contact here?
Okay, so currently we have cooperation with two clinics, one from Poland and one from Spain. However, I will admit here that for now, the neurosurgeons are not directly in the loop. Before we can proceed to have them in the loop, we need to have this system, I would say, in a stage that is ready to be used by them. So we need to have this web-based tool so they can verify and they can propose what should be improved. Because as far as I believe, here I'm open for discussion, the surgeons, they cannot really help us with the deep learning based development, I would say. They can help us with analyzing the results. They can help us with verifying whether the outcomes are acceptable from the clinical point of view. But that's something that will happen later in the project. So far, we have several suggestions.
Okay.
Sure, go on.
Okay, I think that's a point for discussion. I'm very often have with Sano as well. So the question is, at what point is a good time point to get, let's say, some kind of constraints from the clinical settings? So in your example, let's put it like this. So you have a point-based technology. I saw some wavy patterns. I don't know how smooth, for example, a solution has to be or how regularized. You say you have different materials here that may impact that the shape, let's say, the exactness of the shape may not be the only constraint. Maybe for certain materials, you have to be thicker than the original bone material or something like that. The question is the overall shape correctness the important thing, or is the boundary correctness when setting in the implant the more correct measure for clinical? And how correct? So what is it? What is a threshold that you have to cross in order to be clinically acceptable for them? So all those things, I think, require normally that you are involved with the clinics much earlier than the other thing is you claimed you want to do it in real time. Yeah. So given that the 3D printing of titanium, for example, takes a whole day in order to be done, that is not something that you can apply in the emergency surgery that is probably starting the whole thing. So I see several things that would require some feedback from clinicians in the early phase, or
okay,
am I wrong?
I will answer these two questions separately. So about this feedback from medical doctors, actually, it's not that we have not asked any questions, that, you know, we are silent and we are not asking anything. Actually, we ask some questions. For example, the doctors from the hospital of Krakow at Prokocim. And we have some initial feedback. We know what we need to focus on. For example, we need to focus on the mounting points. We need to focus on the thickness, as you mentioned. That we need to basically make the methods adaptable. So the neurosurgeon, they want the capability to define the thickness of the implant, and we are aware of this. So we basically performed the initial questions, so what they would really like to have. So we are more or less aware of the, I would say, initial demo that we need to deliver the initial product before we can continue to talk with the doctors further. In terms of the importance of particular design choices, actually both the shape of the overall implant as well as the connectivity with the bone are very important. That's because the overall shape is very important due to the psychological point of view, because people want to look normally. That's the first thing. And the boundary joints, they are also very important because, for example, for small implants, for example, for people that live in northern countries, that can be printed using, for example, the PIC material. We don't need to have any fixation for the implants, especially the implants are usually smaller. But in contrast, for example, for the titanium, as you mentioned, this is not really the case, because for titanium, the implants, they need to be much thicker, and moreover, the mounting to the skull is a bit different. We need to use screws to mount this. So actually, we analyzed all of this. So we had initial talks with the neurosurgeons about all these details. However, before really taking them in the loop, we need to have at least the minimum working product before being able to really take their time, because you know, the experts they are not free. They are not, I would say, available. So every hour of the neurosurgeon time is extremely pricey, and we need to use this carefully. And we don't want to waste their times with some silly questions.
Yeah, okay, I understand that fully. So, okay, second question. Well, if we are in prosthetics, I would say the workhorse currently is rather statistical shape analysis, shape models, and I think Piotr, you pointed out, is working along those lines as well, if I'm not totally mistaken. So, is there a reason to go the non-standard way here? Because I think if you are going to apply for let's say certification or so, it would be much easier if you would have something that is very established in the prosthetics industry, isn't it?
Yes, I agree. But here I have a nice counter-argument, I would say, because we compared our approaches to different researchers that use the statistical shape modeling on the same data sets, and our results are simply superior to them. They cannot go beyond certain level of quantitative results. Moreover, even though it is quite counterintuitive, but the statistical shape modeling is also not generalizing that well into real defects. That's why basically the deep learning based modeling outperforms these kind of methods by a huge margin.
Well, there is, of course, also deep learning for statistical shape modeling, but yeah.
And we also outperform them. So there is a paper that we cite in one of our papers, and basically our results are much better.
Okay,
But I agree, of course.
I just saw your metrics, and well, you didn't cite the Freiburg people, and I think they have impressive results on cranial reconstruction and with statistical shape modeling. So, well,
So I
they
think
didn't
I'm
participate
missing.
in the competition. So I think there were only 3 competitors in the competition you were citing. So
No, there were 8 competitors.
8. Okay. Okay.
Or even 11, I believe. It depends on their. I think there were 11 and 8. I'm not aware of any work from Freiburg about this. I'm aware about from people from Basel actually working on this.
Yeah, I know.
But no paper from Freiburg I have seen.
Yeah, they have a couple of those. Yes, Füsenegger et al. So I would recommend that.
So I assume that probably simply maybe the keywords are different, so I cannot basically find them, or maybe they do not cite the papers I'm citing. So basically, there is no linkage between the research, and that's why probably I missed the papers.
Okay, okay.
Olaf, many thanks. And now we have Maciek in the queue.
Okay, thank you for the presentation. Yeah, I have actually two similar questions. So first one is again about the collaboration with clinicians, and it was already discussed. But one more thing, I mean, you mentioned that, yeah, the doctor's time is very precious, but of course the deep learning engineer's time is also quite quite expensive. But can you say whether you have allocated actually some budget for these clinicians in the project, or do you think in the next projects it would be worth to include such a budget?
So far, I mean, in this particular project, we have very small budget allocated for clinical consultations, but it's very small budget because in this particular project, we wanted to achieve the readiness level at the level of 8. We are not going for 9 for this particular project. And that's something we simply cannot allocate in the LEADER program, because the maximum budget for this project, it was 1,500,000 zlotys, and that's the amount we received. And that's something that can result in the prototype, but it cannot absolutely, it's not sufficient to apply for the medical certification at all. And it's also not sufficient to really incorporate medical experts, I would say, in the loop on the regular basis. For this, if the project, after it concludes, is successful, then we will apply for some additional funding. We are not exactly sure where exactly, when, etc., but we plan to apply for such funding, and then we plan to increase the amount of funding that can be spent on all kinds of medical consultations, and also on the medical certifications. Actually, just as one side note here, here we don't really, from the theoretical perspective, we don't need to have the medical certification for this. We have already contacted people responsible for handling this, and we don't need to register this as medical product because we just need to have to print from medical materials with medical certifications. However, in theory, we don't need to do this, but in practice, no hospital will buy this without the certification. So that's why we plan to actually go for the medical certification, but this is beyond the scope of the LEADER grant. This is a topic for just, I mean, for many years ahead of us.
Yeah, I understand that the final decision whether the shape fits the patient is, for example, yeah, it's done by the doctors anyway. Yeah,
exactly.
So it's not fully automatic, of course, obviously.
No.
Okay, thank you. And the second question I had was more technical. I was interested in this method about using the symmetry, yeah, in this deep learning. So, do you think this could be considered as something, you know, similar to the general topic of physics-informed neural networks, in which you impose some kind of, you know, physical constraints on the model, yeah? So this is, here we have, I don't know, the symmetry is a kind of constraint, but maybe it's just a simple comparison. What do you think?
I mean, I would say yes. I would say that that's true. Here, I would say we are introducing some a priori medical knowledge into the process because we know that the schools should be symmetric, and this is a physical property. I would not say that this is a physical informed neural network. It's working a bit differently, up to my knowledge, but from the, I would say, point of view of the basic principles, then yes, I agree. It's a physical informed neural network.
Yeah, and the kind of follow-up is yeah, maybe I'm totally wrong, but could we try to, impose some additional constraints, like something maybe from this statistical shape modeling or some ideal, shape modeling that, or idealized, shapes that could also help in this process further?
I think so. I think so. It should be possible, but I think it strongly depends on the particular property we would like or constraint we would like to enforce. But here, both can be introduced both during training and also during the instance optimization. Because here we are using one, I would say, objective function, but the objective function, actually two, because there is regularization and the symmetry loss. But we could as well introduce any kind of physical constraint in the optimization process. It's not a problem. But here, basically, in this particular, I would say, application, on the defect reconstruction at least, it's simply not, I would say necessary. Of course, during developing, and that's something we are currently also working on, during transferring the defects into personalized implants, actually, then the problem will be much more important because then, for example, we need to really use the physics or, for example, online methods for checking the mechanical response, some finite elements, for example, to ensure that the, I would say, the connectivity between the implant and the bone and also the thickness is acceptable from particular point of view of particular material and particular neurosurgeon.
Yeah, that's an interesting topics. Okay, thank you very much.
Thank you very much. We have Wiesław now.
Okay, hello, can you hear me?
Yes.
Yes.
Go on,
Okay,
please.
fantastic. So maybe first I start with a comment which is aligned to Maciek question comment. So in my opinion, you don't need any funding to work with neurosurgeons. What you need to excite them that the project which you are doing is useful to them. And in such a case, they be working with you, giving you any advice. I used to work with the most expensive American neurosurgeons. I never pay a single dollar. So, but of course, if you want to achieve that, you need to find them. If you go to Mikai, you won't find them. If you go to clinical meetings, if you show what you have, and if you get them interested, believe me, they come by themselves, they spend time with you, they give you advice, they give you guidance. So this is my comment. And my question is aligned with what Olaf also tried to ask, because if you are doing something exciting for you, if you feel that, okay, it generates papers, okay, I will check it with doctors, maybe later, later might be too late. Somehow, frankly speaking, I didn't understand your approach, because what you are doing, you are fitting the implant to bone. You can do that at the border, but within the implant, you can fit it to the shape of the brain, meaning you need to use MR. You don't use MRI at all. So how come that you are trying to fit something to the actual brain and you don't use the brain data? Yeah, symmetry might be good, but might be not sufficient.
Okay, so
this is for me paradox. That the implant is supposed to work for the patient, and on the other hand, you don't use the patient's full information.
okay, so here I will answer both the question and the comment. So starting from the comment, yes, actually, we are planning this year to go for a neurosurgeon dedicated conference to show our, I would say, current status of the research, and because we believe that at this stage, actually, it's ready to be presented to a wider audience of clinical doctors, and we hope that maybe some people will be interested enough to to also join our team and to consult the project. However, we have some experience with doctors from Poland. Actually, maybe they are not, I would say, the best known doctors worldwide. But apparently, I will not say the names here because it would be very rude for me. But in Poland, only one single doctor from Krakow accepted to basically consult us, to work with us without salary. And all other doctors, the first question was, yes, but what will be our salary for all of this? So unfortunately, maybe that's true, but I would say not in Poland. Apparently, the goals of the doctors in Poland are a bit different, I would say, than in the world. So we hope that maybe in an international conference we will meet somebody that really would like to do this. For example, in exchange of authorship in scientific paper or something like this, without getting paid enormous amount of money. And now, in terms of the question. Yes, I agree. I agree that we need to ensure that after the reconstruction, that the implant is basically not connect. I mean, maybe not connect is the wrong word. It's not overlapping with the brain. It's also very important because, for example, the brain, there may be some brain swelling, for example, that we also need to take into account. All of this is true. But actually, we assume that the swelling is already out. So the brain is basically not directly in the cranial cavity. And based on our consultations, it's correct for majority of the cases, not for all the cases. And that's these cases unfortunately need to wait before the swelling stops. But of course, we can use the patient data. We can simply perform the brain segmentation. And after we perform this initial defect reconstruction, we can verify whether this reconstruction overlaps with the brain. That's something actually very, very easy. And that's something we are doing, but we are doing in our second step of the pipeline. So firstly, we start with the defect reconstruction, because if we have the reconstruction, I would say partially okay, if the defect reconstruction is in good place, if the shape of the defect reconstruction is close to the original cranial cavity, then in the second step of the personalized implant refinement, we can very easily introduce the patient data into the process. And that's something we are currently working on.
Okay, yeah, because this, what you are calling second step, might be the first step for the neurosurgeon. Otherwise, if the fit is not good, you can cause the patient to got stroke. Another question is again, it's about positioning of this work. So what I have in mind is that cranial implants, it's not something which exists for 10, 20 years, but what about 100 years? And there is pretty big competition. There are companies like Stryker, which have been doing that for decades. So how your methods, you think it's going to be superior? From the point of view of surgeon or patient, the fact that you are using deep learning, it doesn't translate that your method is better, more accurate, cheaper, less invasive, and so on. So can you justify your approach from this perspective? Especially that in the team, I see that you have a person involved in commercialization. So of course, this is something which, if you plan to market it, it's critical.
Okay, so in terms of commercialization, actually, we have one person that is expert in this field. It's Daria Hemmerling. She already commercialized, I would say, a lot of products. Also received medical certifications, patents, etc. But in terms of commercializing this particular product, there are very big medtech companies like Stryker. I think even more importantly, Materialize, Mimics, that produces software that directly is suited to the CAD modeling of cranial implants. But before applying even for the funding, we performed very strong research on the market, and no company currently offers ready-to-use product that can model implants, personalized implants in just one single click. They require to be used by experienced biomechanical experts that needs to use this software to simply model the implant, to take into account all the factors. And this is costly. I mean, the time of these experts is costly, and that's the main reason why people wait so long time nowadays for the reconstructive surgery, because they undergo the cranial damage. The CT scan presenting the skull after the damage is available just immediately after the damage. And then it's transferred to a particular external company, mostly, not always. Some hospitals actually do this by themselves, but in most of the cases, it's transferred externally. And then it's being modeled, then it's manufactured, then it's sterilized and transferred to the hospital. And this takes so much time. So in our, I would say, philosophy is to transfer this step directly to hospitals. So directly inside of the hospital, for some patients, it will be possible to apply this directly during the primary surgery. Of course, not always, because, for example, as is mentioned, very big cranial damages, for example, requiring titanium implants, it will be impossible. But at least for some of them, it will be impossible. It will be possible. And the main benefit of our approach is simply the speed of the reconstruction and the cost of the reconstruction. We can achieve the same using biomechanical experts. They will propose also very nice, maybe even slightly better implants, but the costs associated with this and the waiting time is just enormous.
Okay, so thank you and good luck.
Many thanks, Wiesław, for participation. Olaf, you have your hand still up.
Oh, sorry, that was oversight.
Okay, but anyhow, well, we have almost reached the time devoted to our seminar. So many thanks to Marek for the talk, and all of you to taking part in this, and to Olaf, Maciej, and Wiesław for taking part in discussion. Many thanks. Thank you very much.
Thank you.
Thank
Bye.
you. Bye.
Goodbye.